Good day, everyone. Our topic for today is all about the Bernoulli's principle. Bernoulli's principle came from a person named Daniel Bernoulli, which states that the faster the fluid moves, the less pressure it exerts. Now, let's delve into Bernoulli's principle, a fundamental concept in fluid dynamics that reveals a fascinating relationship between fluid speed and pressure. Bernoulli's principle states that as the speed of fluid increases, its pressure decreases, and vice versa. In other words, there's an inverse relationship between the speed of a fluid and the pressure it exerts. So, class, how airplanes fly? Anyone? Well, wing is curved on top, right? So the air makes it over the top and bottom at the same time. Air must move faster to go over the top. It is because the top has less pressure because of Bernoulli's principle. So there are forces combined that allow an airplane to fly. So first we have lift, the upward force in flight. In normal flight, lift equals weight of plane. Second, we have the thrust, the forward force on the plane. Normal flow of air over wings will not allow a plane to have enough lift to take off. Plane must reach a certain speed and create enough airflow around wings to fly. This is done by thrust of the engine. Understanding Bernoulli's principle provides insight into a wide range of phenomena, from the flight of birds to the operation of carburetors in engines. As we explore practical demonstrations, keep in mind that these principles impact on fluid dynamics and its application in our everyday experiences.
What will happen if we create a strong airflow between two balls suspended on threads? It seems that the flow should push the balls apart. We switch on the blower and, surprisingly, the balls get attracted by one another. They are rotating, which means the airflow is getting through between them. Why isn't it pushing them apart? Let's carry out another experiment. We attach a funnel to a hose and switch on the blower. Then we put a rubber ball into the funnel. Instead of bouncing out of the funnel, it gets sucked into it. We turn the funnel upside down, but the ball isn't falling out of it. So why does the airflow hold the ball in the funnel instead of pushing it out? A similar experiment can be conducted with running water. If we put a tennis ball next to it, the ball sticks to the water and hangs there on an inclined thread. It looks like a fast flow of gas or liquid possesses counterintuitive properties which need to be explained. To do so, let's consider water flowing through a pipe of variable cross-section. When the cross-sectional area of the pipe decreases, the speed of water flow increases. According to Newton's second law, in order to increase the speed, some force must be applied to water. Thus, the pressure in the wider part of the pipe must be higher than that in the narrower one. Therefore, when the pipe gets narrower, the pressure in it will not rise, as it may seem at first sight, but fall. This puzzling paradox is called Bernoulli's principle in honor of its discoverer, a Swiss physicist Daniel Bernoulli. We made this narrow neck pipe from 2 plastic glasses. When we blow it, the air pressure at the exit will be equal to the atmospheric one. This means that inside the narrow neck it will be lower than the atmospheric one. To check this, let us insert a tube into the wall of the neck, connecting it to a pressure sensor. When we blow the pipe, the sensor shows the decrease in pressure by 5 kilopascal, which is 50 centimeters of water column. Let us put the lower end of the tube into the vessel with colored water and blow the pipe again. We can see that the water makes a 30 centimeter rise. To increase the pressure even greater, we'll connect the pipe to the blower, which provides a far higher speed of the airflow. We switch on the blower, and what we get is a perfect water sprayer. Now let us attach a plastic bottle to the pipe and switch on the blower again. That's incredible! A decrease in the internal pressure causes the bottle to be crumpled by the outer atmospheric pressure. Let us consider water flowing inside a cross-section pipe. The volume of water V enters the pipe from the left end and leaves the pipe on its right end. The difference of pressures at the ends of the pipe does mechanical work, which equals P1 minus P2 multiplied by V. When there are no losses, all this work goes to increase the kinetic energy of water. Mass is the product of volume multiplied by density. In this case, the volume decreases, so we can rewrite the formula in the following way. The value of rho v squared divided by 2 is called the velocity head of a fluid. According to Bernoulli's principle, the sum of pressure and velocity head in an ideal fluid remains constant throughout the whole pipe. This equation allows to measure the speed and volume consumption of a gas or fluid flowing through the pipe. To do this, a special device is inserted into the pipe. It is called Venturi tube by the name of its inventor. A differential pressure sensor is attached to the tube. It measures the difference of pressure between the narrow and the wide sections of the pipe. The speed of flow calculation is based on this difference. Let us switch on the blower. The device shows that 12 liters of air get through the pipe every second. This means that if the section of the pipe is 3 square centimeters, the speed of air within it is 40 meters per second. Industrial venturis look much more substantial. They can measure the consumption of gas flowing through the pipeline with minor pressure losses.